I'm sharing my screen. Yeah, yeah. Okay. So basically, we are the Gnanodaya VLSI technologies. So I want to explore what are the job opportunities in VLSI or semiconductor industry. So basically, these are the things I want to explain today. So after completing the session, you can ask any doubts or any queries. Okay. Yeah. So if you see this. Basically, in the semiconductor companies, in the semiconductor, they are broadly classified into three. Okay, so those are nothing but we call as product-based companies, service-based companies, and EDA companies. Okay, product-based companies are nothing but the companies which will produce the ICs. Okay, suppose product-based companies, if you say. If you take the product-based companies, around 20 plus product-based companies are there. Okay, so so that means Intel. Okay, Intel will they will produce. So nowadays you are using in your laptop or desktop that Intel process, no i5, i3, i5, i7 process. Okay, and Samsung. Okay, TSMC and Micron, Qualcomm, Nvidia. Okay, so nowadays we are using in the mobile the Qualcomm Snapdragon processor, Nvidia, Broadcom, okay, MediaTek, AMD, okay, AMD Ryzen processors also there, okay. So Ryzen processor, Ryzen 3, Ryzen 5, and Ryzen 7 processor you are using in your laptop, and Infineon, Apple, ST Microelectronics, or NXP analog devices. Like this, you have 20 product-based companies are there so globally and service-based companies means they will not produce any they will not produce any products, just they will give service related to this whatever the service. Okay, I think you came across some service-based companies like Wipro, HCL, Infosys, Capgemini, okay, and L&T, Mindtree, okay. uh, Samsung, okay, UST Global, Sankalp. So apart from this, you have 100,000 plus service-based companies. VLSI companies are there in there all over the Hyderabad, Bangalore, Noida, and India. Okay, so this is service-based companies. Okay, what are these EDA companies? EDA companies are nothing but so this is EDA. EDA is nothing but electronic design automation tool. Okay, design automation means, so basically in the VLSI, if you take first you have LSI, okay, SSI, small scale integration. Small scale integration means you have only some 10 transistors are there. Okay, and next you have medium scale integration, large scale integration. Okay, very large scale integration, and ultra large scale integration, and giant scale integration. Okay, so that means 100 or 1000 transistors are there means manually you can do the whatever the design or whatever the layout and whatever that manually you can do. But VLSI is nothing but you have we can say like 100 billion transistors. 100 billion transistors means 1,000 crores transistors are there in an IC. Okay, so 1,000 crore transistors are there in an IC means manually it's not possible. So you need to use some EDA tools. Okay, EDA tools are there in front end and back end. The companies which will provide these EDA tools are nothing but Cadence. Okay, for the front end you have some front end and back end you have EDA tools. Okay, and for the front end you have Cadence Exilium, or Cadence for the verification you have Cadence Jasper tool. Okay, and in the back end for the physical design you have you have Cadence Innovas tools. Okay, like that. And Mentor Graphic also provide these EDA tools for the Verilog model sim, and for system Verilog and UVM we have Quasta sim. Okay, and Synopsys also will provide the yeah, front end and back end tools. Synopsys for the front end, it will provide Synopsys VCS tools. Okay, so that means the companies which will provide these electronic design automation tools. Okay, AMD also provide that is for the front end. For the Verilog simulation, you have Xilinx Vivado tool. Okay, so from that you can get the circuit. You can get the circuit and you can simulate. That is functional simulation. Okay, so these EDA, so whatever the EDA product or service-based companies will always be synchronous. So that means always combine together to meet the technology deliverables. Okay. So with the support of whom VLSI engineers. Okay. So that means here EDA tools we can't write with AI. Okay. So we know we want the VLSI engineers. So this VLSI engineers, what they will do, like they will. My voice is clear now. Just anyone give response so that I will move forward. My voice is clear now. Okay, thank you. Okay, yes. So as a VLSI engineers, what we are doing means we are giving some guidelines to the tools such a way that this tool will work. Okay, without VLSI engineers, this tool will not work automatically. It will not work. Okay, we need to give some guidelines to these tools. Okay, suppose if you want to write a Verilog code, okay, you need RTL code. So you need to write the code and you need to simulate. Suppose if you want to do verification, you need to use system UVM related or system Verilog concepts. They need to verify each and every corners. Okay, all those things are done by the physical design, also done by the physical design engineers. Okay, so this is about the VLSI company. And next, so coming to the VLSI design flow. So basically, like VLSI is divided into like analog and digital. Okay, so that means in the universe, in the outside, in our earth, so all the signals are like analog in nature. Okay, it may be sound, or it may be temperature, or it may be anything that is analog in nature. There is a there will be a transducers that will convert analog to so this whatever the physical quantity into electrical quantity, and then again and that is ADC. So that ADC is converting analog signal into digital signal. Okay, so there are some analog engineers are there. Analog engineers, what they will do means they will work under the transistor level, and they will do the layouts related that. Okay, they will do the layouts and all those things, and they work on the transistor level. Okay, those we call as analog engineers. Okay, so whatever the analog blocks are there, they will do only on the analog related. And this is nothing but this flow is nothing but digital. This flow is nothing but digital. Okay, so basically, in the VLSI, what are the target devices are nothing but VLSI. You have ASIC and FPGA. What is this ASIC and FPGA means? ASIC is nothing but this is used only for the particular application. Coming to the example, suppose in your household, normally your LED TV is there. LED TV is nothing but one ASIC. Okay, so so here day by day in olden days, before 15 years like that, you are using some CRT like olden TVs, no? So that will take more power, like 230 volts or 250 volts. Okay, but your TVs, your LED TVs or smart TVs are there. It is taking the power of only 12 volts. Okay. So due to what it is taking low power means due to VLSI only. Okay. So ASIC is nothing but it will do some specific application like washing machine or microwave oven or refrigerator, or it will do the only you can't replace the ICs present in the washing machine into your TV like that. Okay, that IC is you only use it for specific application. And in the automobiles also. So in automobiles also, you are using this ASICs. Mainly, we are using for we call as in airbags or auto lock braking system or speed control system. So that is nothing but these ICs are mainly used for only specific application. That is nothing but ASICs. Okay. And coming to this FPGA, FPGA is nothing but this we can program. This we can reprogram. Okay. Suppose if you want to design some FSM. Okay, the like you can write the Verilog code and you can port into this. You can generate the bit stream file and you can load into this FPGA. Okay, so so again, suppose if you want to do for counter, you want to write the code for the counter. So you can erase this and again you can write the code and you can generate the stream and you can reprogram. So mainly we are using in R&D purpose. Okay. So R&D related and FPGA we are using in the defense, okay, defense and telecom, like towers are there, no towers, okay. So why? Because suppose every time the technology is changing means you can't, so that defense related equipments are there, those are costly, okay. So you can't, what we call, we can't purchase every time, no. So like, so depending on my technology, you can program this, okay. So that is FPGA, okay. So coming to this ASIC design flow. So basically, like if you consider first design specification means suppose if you take the one IC, okay, one IC. So first you need to decide that IC is that your VLSI IC is used for which application. That means it may be useful for computer related application, or it may be useful for we are going to use in communication related or network related. Depending on my application, I need to like check for how much area it will take, how much power consumption it will take, how many inputs and how many outputs. That will be done by the design specification, okay, and design specification. And so how the specification is done means, in the high level there are architectural engineers are there, okay. Those are very experienced engineers. They will make this specification. They will take the specification from the client, and they will make the planning and architecture, all those things, okay. So those are very much experienced, okay. Architecture is nothing but, suppose if you want to design a CPU, okay. CPU means, so that means you do architecture. How many inputs are there? And in CPU, you know that you have ALU and control unit, memory unit, and bus interface unit. All those things are there, no? So that means you do the both this architecture of the CPU. Okay, you do the architecture of the CPU, that architecture. Okay, and after that, what you need to do? So micro architecture. Micro architecture means sub-blocks architecture. Sub means like we'll come with, so first we'll design the ALU, okay, and we'll design the control unit, we'll design the memory unit, and we'll design the bus interface unit. These are nothing but micro architecture, sub-blocks, okay, sub-blocks. So suppose memory means, again it consists of data memory and program memory. So you need to design RAM as well as ROM. So you need to design the micro architecture. So whatever the sub blocks are there, those are nothing but micro architecture. So basically, like in VLSI, you will come with hierarchy. Hierarchy. Okay. What is this hierarchy? First, system on chip. Okay. Next, you have system on chip, and next it consists of some processors or peripherals. And next, you have modules. Okay, modules are nothing but it consists of combination or sequential circuits. And next you have gates, and next you have transistors. Okay, so it may be top down approach or bottom up approach. So in the VLSI we'll follow top down approach. Okay, first we want to design the higher level SOC, and next SOC is made with some processors and peripherals, and these peripherals or processors are made with modules. It may be combinational or sequential. Again it may be made with gates are made with the transistor. Those are nothing but CMOS. Okay, so this is about the hierarchy in the VLSI. Okay, so we'll come with top-down approach. Okay, next you have RTL design. RTL design means, so like in programming language, you have two languages are there, like software language and hardware descriptive language, HDL. Okay, software language means they will not provide any hardware. Okay, they will not generate any hardware. Just they will what we call they will provide the application for that. Suppose like banking is there, so the software people will create a software for the banking related operation. Okay, or railway ticketing is there. They will create a one application for railway ticketing, and based on that application only, these railway people will make use that application and give the print the ticket and give. Okay, they will make only application. This hardware descriptive language, we can make the hardware. We can make the hardware. Okay, so basically there are two types of HDLs are there. So HDLs. So one is VHDL and Verilog. HDL and Verilog. Okay, this difference I will tell you. Just I am discussing about this Verilog. Okay, so Verilog mostly it is operated in four modeling styles. That is switch level modeling, switch level, and next you have what we call switch level, gate level, and data flow level, and behavioral level. Okay, so here these are not converted into hardware. There is a term called synthesis. Synthesis is nothing but by using synthesis, you are converting your HDL into gate level netlist. Gate level netlist. Okay. So what is this HDL? You already studied the digital combinational circuit, sequential circuit. You studied so many modules like half adder, full adder, comparator, decoder, encoder, and in the sequential circuit like latches, flip flops, counters, FSMs, serial adder. So that you are describing in terms of programming is nothing but HDL. Okay, you are describing your hardware in terms of textual format is nothing but HTL. Okay, so here RTL is nothing but you are writing in terms of data flow modeling and behavioral modeling. Data flow modeling means in terms of expressions you will write. Suppose like AND gate is there. AND gate expression you know. So that is Y equal to what? A and B. Okay. Behavior means suppose half adder is there. So with I know the behavior of the circuit. I am not take caring of internal circuitry. I need to use some procedural assignments like if case, those statements. So if you are comfortable with C, you can write. Okay. So RTL designers, so this RTL is nothing but register transfer level. So mainly how the data is transmitting through the registers. Okay, registers. So internally it is converted into flops. So how the data is transmitting through the registers is nothing but RTL. Okay, so this RTL design engineers will design by using Verilog code. Okay, RTL designers will write the Verilog code. Okay, will write the Verilog code and they will design. Okay, and this Verilog code we can verify. Okay, we can write the test bench. We can verify up to FSMs only. Okay, up to FSMs we can verify. But suppose if you go for complex blocks like intellectual properties or system on chip, okay, so it is hard to verify. So you need to go for RTL verification. RTL verification is nothing but you will use system Verilog and UVM. Okay, so basically, like the system Verilog, some more properties will be there compared to Verilog. Like you have randomization, polymorphism, constrained randomization, and OOPS concept will come. Okay, so arrays are there and structures are there and two-state data type is there. So that you study in the system Verilog, and next. There is no particular thing for test bench. Okay, there is a common thing for test bench. Suppose in SV, suppose if you want to write the test bench for I2C, separately you need to write for like SPI. Okay, so there is no like reusability is not there. Okay, that's why so companies used one type of test bench, that is nothing but UVM is nothing but this is not a methodology. Just this is a methodology. This is not a language. Okay, this is a language. This is HTL. Okay, we can design by using SV also. Okay, so this is a methodology. Methodology we are using SV in the UVM. Okay, universal verification methodologies. some standard libraries are there in the UVM factory that you are using in the UVM, and you can write the test benches, and reusability is there. Okay. So here RTL verification, you have SV engineers. Okay, design verification, DV engineers. So DV engineers, what they will do, they will whoever the design this RTL design, so these DB engineers will test each and every corner cases, okay, and they will rigorously verify your design is meeting your specifications or not, okay. Rigorously, these DB engineers will verify, okay. They will use this UVM and OVM and all those things, and they will verify DB engineers, okay. So we call as ASIC DB engineers also. So if design is met, it will go to the next state. If design is not met, it will go to the initial RTL. So this both will work together. Okay, these RTL engineers and design verification engineers were work together. Okay, like that. Okay, and if design is met, it will go to the next state. Okay, next state, and there is a logic synthesis. Synthesis engineers are also there. What is this synthesis engineers are there means here in the RTL design you will get the netlist. You will get the netlist. Okay, hardware. But this is non-optimized. Non-optimized. Okay. This non-optimized, we need to do the optimization by using synthesis. There are the synthesis engineers are there. They will work under the constraints. What are the constraints? Constraints are ATP, area, time, and power. Okay, these they work under the area, time, and power constraints, and they will make the netlist. Okay, they will make the netlist. Okay, so the output of this synthesis is optimized netlist. Optimized netlist. Okay, netlist. And next you have a DFT. DFT is nothing but design for testability. So design for testability, you have DFT engineers. These engineers, what they will do, they will test your design whether your design is meeting your specifications or not. Okay, so they will provide some scan test, built-in self test. Okay, some techniques they will use, and they will give the test vectors. Okay, so this is DFT. And next you have LEC, logic equivalency check. Okay, logic equivalency check. So you are checking your logic equivalency whether your design is meeting your specification or not. Okay, that is logic equivalency check. Okay, and next you have STA. STA is nothing but static timing analysis. Static timing analysis. Okay, static timing analysis is nothing but suppose in digital you already seen that. Suppose if this is a one AND gate, you are getting AB and Y equal to what? AB. Okay, so you are getting the output at a zero simulation time. Okay, 0 seconds you are getting the output, but there is some propagation delay for this AND gate. Okay, so when you are considering this propagation delay, okay, when you are considering the propagation delay, and there is setup time, okay, setup time, hold time, and clock skew, okay, clock skew and clock jitter. So all these delay related things will be done in the STA, static timing analysis. Okay, so here you can like in the RTL design, when you are doing this test bench, so simulation by using waveforms you can see that, but simulation is not that much required. That's why you need to go for this delay related, that is static STA engineers. So STA engineers will do this delay related things. Okay, STA engineers, you have STA engineers. Okay, and STA is there in pre-layout STA. After layout there is a post layout STA. Okay, pre-layout STA and post layout STA. Okay, and next you have this PD flow. So PD flow means suppose PD flow means physical design. This is back end. Okay. So up to synthesis, this is front end. Okay. So up to synthesis, this is front end. And PD flow is nothing but that the DFT and LEC and this HTA will come to the back end. Okay. So PD flow, if you see, so PD flow means you need to do like I'll tell you with one example. Suppose if you want to build any building, Okay, civil engineer is there. First what he will do some planning, no? So he will do some planning, how the building should look like. Okay, like that. So they will take the input from the front end engineers. Okay, so front end engineers, and they will do the some partitioning. They'll do the partitioning. That means where the macro cells should be placed, and where the these modules and where the IO block and all those things. Okay, and they'll do the floor planning. Okay, how the die size will be there, how the so things are happening. That floor planning they will do. Okay, and power planning related. Power planning means you need to do some power related things, that there you will do the power planning, placement, clock tree synthesis, routing is nothing but connections. Okay, clock tree synthesis is nothing but all modules will not work at same clock, no? So there will be some master clock or global clock, that will be divided there will be some clock dividers will be there, and each module how much clock frequency it is operating, that much clock you can distribute. Okay, and timing closure. So all this will be done by the PD engineers. Okay. So this is backend. Okay. So if you see this PD. So this is nothing but physical design. Physical design. So this is nothing but we can call as PD engineers. Okay. So you have PD engineers. PD engineers. Okay. So PD engineers will take care of all those things, PD related things. Okay. This is backend only. Okay. And next, parasitic extraction means inside so many, like in the when you are doing this PD analysis, inside so many metals will be there. Okay, so metals are like metals are between the two metals with so much short distance will be there. So that copper metals have some resistance and capacitance RC values. Okay, so the extraction, how much R and C values for that metals is nothing but parasitic extraction piece. Okay, so but that is nothing but parasitic extraction. And next, next, after doing this post layout STA, if design is met, it will go to the this physical verification. If design is not met, again it will go to the PD flow. Okay. So if design is met, again you need to do physical verification. Okay. Physical. You have PV engineers. Okay. You have some PV engineers. Okay. So PV engineers, what they will do, like they will do some checks. Okay, some checks that they will verify, like your chip is following, means meeting you this specifications or not. Okay, specifications are not, like this, they'll do the PV units, and after that it will produce some GDS2 file. GDS2 file will be given to fabrication. Okay, so in the fabrication, based on this GDF2 file only, they will do basic fabrication, like CMOS fabrication only, like N well well technique, twin tube technique, and so many fabrication like diffusion and implantation, photolithography, all those things are there. They will do the some fabrication. Okay, after fabrication, again they will send this chip to the designers. Okay, so that chip, whatever the chip is there, that chip they will test whether this chip is meeting these specifications or not. Okay, if it meet, they will check in all the cases. Okay, chip level testing. Okay, so that means if it is meeting all the cases, it's okay. Suppose anything it's not meeting, again that bugs, again they will send it to fabrication. Again fabrication will take care of that bugs, and again they will make according to this. Okay, so this many flows are happening into this. Okay, so this many, like so many, like 10 to 15 VLSI engineers are there for making one IC. Okay, one person will not do this IC, no, one company will not do. So each and everything, every module or everything, you have different engineers are there. Okay, so why this much design flow is happening means, so any IC is coming out, okay, coming out into the real world. Okay, so any IC is coming into the real world. Suppose that IC is using in the aircraft, okay, in the airplane you are using, okay. Suppose something happens due to defects in that IC, so it will damage to not only the property, it will damage to so many lives, okay. So that means whenever the chip is coming into this market, rigorously it will take around 1 year of time, I think so. It will take 1 year of time to come into market. So this many steps it will do. Okay. So this is nothing but ASIC design flow. Hope you understood. Yeah, I will move forward. So I told you, no. So floor planning. Floor planning means I'm discussing about physical design. Okay, physical design. That means partitioning, floor planning, power planning, placement, clock tree synthesis, routing, and timing closure. These all are there, no. So I'm discussing about that. See here. So floor planning. Floor planning is nothing but planning your floor. Okay, floor being the die. Die means there will be like it will be like a CD. Like this is nothing but one die. Okay, in this die we can fabricate so many processors. Okay, so you'll estimate the die size. You'll estimate the IO or micro placement. Planning of power distributions, all those things will be done in the floor plan. Okay, so these are the goals of floor planning. Okay, all macros in placement grid, no macro overlap, no PG nets. DRC is nothing but design rule checks, and LVS is nothing but layout versus schematic. Okay, is there any violations are there? Okay, design rule checks means it should satisfy the area width, dimensions, and what are those. Okay, and whatever you are doing the layout, that is matching your schematic or not, that is LVS. Okay, and minimize the congestion and make the ensure design is routable, make sure the design timing is meeting. Okay, all those things will be goals of floor planning. Okay, so what are the inputs for PD means one input is I told you synthesis, no. I told you synthesis. Synthesis is nothing but you are converting your HTL into gate level netlist. Gate level netlist. Gate level netlist is nothing but what this is in terms of gates only. Okay, your circuit is in terms of gates only. So that is .v file. .v file is gate level netlist. Okay, I told you about the synthesis. No constraints. What are the constraints? ATP. ATP is nothing but area, time, and power. Area, time, and power. These are nothing but constraints. Okay, these are coming from the HDC file and some logical library file and some physical library file, LEF file, and for multi-voltage domain design file. So PD people will take the inputs, all the input from the front end. Okay, front end people. So this is the floor plan. Okay. So in the floor plan, you need to estimate the die size by minimizing the core area. This is my core area. Okay. Actually, this is my core area. I need to place the macros, means macros, either it may be RAM, ROM, or processor. Okay. Like this. Okay. Planning the core area, different IPs. I told you, know, IPs means what? Intellectual properties. IPs is nothing but it is available in terms of RAMs. RAMs, I2C, SPA, okay, UART. These all we call as IPs, intellectual property, okay. And the planning for IO pads, power planning, all those things we'll do in the floor planning, okay. And IO planning means we'll receive three different types of input from FE regarding the 5O ports, okay. So different types of inputs you are getting like from the address bus, data bus, and from control signals, okay. So how you are planning this is nothing but IO plan. And floor planning is nothing but floor. What are the floor planning elements means? This is total my die area and standard cells. Standard cells means like standard cells are available in terms of what we call and NAND gates, NOR gates, and flip-flops, okay, flip-flops, adders, okay, those are readily available. Those we call as standard cells. Okay, standard cells are readily available that you can include in this standard cells. So we need to access the area and dimensions on that on this. Okay, These are the and these are the floor planning elements. Okay, placements means so this gives the exact area of core area of all standard cells. Okay, that is nothing but placements. Okay, it will show exact area where I need to keep the standard cells. Okay, and all instance of soft modules will be spread in core area. Okay, there is some core area will be there. Okay, so what are the goals means it will utilize less utilization jump, no convention, no overlaps, good timing values. So these are so this whatever I'm telling, you are going to study in the PD physical design. Okay, in the back end. Okay, placement. And clock tree synthesis means I told you, no, there will be some global clock. Okay, master clock will be there, and that will divide into different modules. So different modules will be operated at different clock frequency. Inside there will be a clock divider will be there, and that will distribute to different modules. Okay, so this is about clock tree synthesis (CTS). Okay, routing is nothing but connections. Okay, so you need to create the global track routes. Okay, and how you are doing the connection between signal pins and metal layers. Okay, what so how you are connecting logical connectivity, physical connection connectivity, and you need to trace out the design rule checks. So all those things will be done in the routing. Okay, connections. Okay. Sign off checks means you need to like so the speed engine is only after routing they will do the sign off checks. Okay, so for sign offs means they will check for each and every electrical sign offs, physical verification, and crosstalk. Okay, so in electrical they will do the power estimation, IR drop, power EM, signal EM. Okay, these are all our sign off checks. Okay, or we can call as physical verification. I told you, no, PV engineers physical verification. Layouts versus schematic, DRC, antenna checks. So all those things are physical verification. Some crosstalk. Crosstalk noise means suppose unwanted signals. Suppose like if you consider some two modules are connecting, so there is no connection between two macros, but two macros are are connecting with each other. Okay, so that is nothing but we call as a crosstalk noise. Okay, so that will be done in the sign off checks and physical verification. Okay, so PD people will do the sign off checks and physical verification. Okay, so this is about the sign off checks and physical verification. So this is about the PD. Okay, physical design is back end. Okay, back end. Coming to the front end, design and verification. So in VLSI, so if wherever you see VLSI, VLSI is there. So suppose you consider your personal computer or laptop or like a digital camera, okay, chips in cell phones, anti-lock brake. I told you, no, in the automobiles also, anti-lock braking system and personal entertainment system and medical devices also. You have ECG, EEG, and measurable devices also. You have logic analyzers. Okay, wherever you see you have VLSI is there. Okay, so without VLSI you don't have the equipments. Okay, so wherever you see, so from day one onwards you are using your VLSI in the household applications. Okay, so here if you see there are, I think you already studied about microcontroller, microprocessor. Okay, microprocessor, and this is system on chip, SoC. What is this? System on chip, and this is FPGA, field program gate array. So microcontroller, I told you, know, microcontroller means in the embedded you already studied, I think. So you studied about 8051 microcontroller. 8051 microcontroller means you have CPU, ROM, standard interface, RAM, timers, IO ports, all in a single IC. Okay, it's a 40 pin IC. Okay, 40 pin IC, and you can use for embedded purpose, embedded systems for specific application. Okay, that is a microcontroller. Okay. Mm. ARM processor is one microcontroller. Okay, so it is operated at 1 megahertz to 300 megahertz. Okay, microprocessor means it will do some general purpose operations like it consists of ALU, register array. I think you already studied about 8086 microprocessor. Okay, so it's a 20-bit address lines and 16-bit data lines, and it's a 40 pin IC, and It consists of some register array, so many instruction sets are there. Okay, and so you already studied about that. Okay, so that is 1 gigahertz to it will what is the clock frequency? 1 gigahertz to 4 gigahertz. Okay, this is microprocessor. System on chip is nothing but so here SoC, system on chip, is an integrated circuit that compresses all the system's required components onto a one piece of silicon. Okay, one piece of silicon. Example, you can say that you have Raspberry Pi is there, no? Raspberry Pi. Raspberry Pi is one system on chip, and Intel i7 processor or Ryzen 7 processor. Okay, these all are nothing but system on chip. Okay, so here like if you see the system on chip, so what are the components present in the system on chip? Like it consists of data processing unit, embedded memory, graphic processing unit, USB interface, video and audio processing. So all these are there. Okay, like you have ARM processor. I think you studied. So this ARM is nothing but advanced RISC machine, advanced risk machine. Okay, so they added some more properties from the risk, and they made this ARM processor. Okay, so load and store architecture is there, and you have some SRAM, flash program, and USART. Okay, Ethernet MAC, SPI, window wire interface, ADC, all these peripherals, USB drive, PWM, all these are connected with a uh, bus called AMBA protocol, Advanced Microprocessor Bus Architecture. Okay, here you have like AHB, AXI, okay, AXI, and APB. Okay, these are all connected with these buses, APB bus. Okay, so high advanced AHB is high performance bus. Suppose if you want to connect with high frequency module with low frequency, you can connect this AHB. If you want to connect with low frequency with low frequency, you can connect with the APB. These are nothing but protocols. Okay, these are nothing but protocols. You need to study about these protocols. And FPGA is nothing but field programmable gate array. I told you, no. So it consists of some CLBs, configurable logic blocks, and IO blocks. Okay, IO blocks, and these are nothing but interconnects. Okay, so IO blocks are connected all sides, four sides it is connected. Okay, and CLB consists of what? CLB consists of lookup tables, and one mux and one D flip flop. Okay, suppose if you want to write the code for AND gate. Okay, so you can write the code by using VHDL or Verilog. Okay, and you will generate the bit file, and you are loading into this FPGA, so that the CLB is acting as one AND gate. CLB is acting as AND gate. And other time you want to design some let us take comparator. So again, you write the comparator code, and you load into this. Again, a previous code will be erased, and it will be loaded like this. It consists of some SRAM cell. Okay, so that means SRAM, I told you, like volatile. Even though the power is on, the that will be code will be there. When the power is off, whatever the code, that will be erased. Okay, like this, you have FPGA. Okay, so FPGA where you are using means, suppose like if I tell you with example, suppose cell towers are there. Okay, cell towers, previously you have 2G, 3G, 4G. Now you are working 5G. Okay, suppose like in 3G, there is some equipment they wrote. So there you are using. Suppose if you are using ASIC in this. Okay, so now the technology is changing. Okay, so technology is changing to what? 5G. Okay, so 5G. So in future it will be 6G. Okay, future it will be 60. You can't purchase whole thing, no. So ASIC means what? Once the program is written, we can't change. Okay, so we need to purchase new one. Okay, so here, so initially when you are using FPGA, What happens? So you return the program for 3G. Now 5G technology came. So what you will do? Just you can reprogram without changing your equipment. You can reprogram. Okay, that is the main advantage of FPGA. In defense also I told you. Okay, so that is the main application. Without changing your equipment, you can reprogram depending on our technology. Suppose future 6G is coming means again 5G technology you can erase, and the 6G technology you can reprogram this. Okay, so you observed or not, before in the ground station always there will be a generator. Okay, so always it should run. Okay, why? Because FPGA consists of some SRAM. Okay, so when the power is cut down, so that will be erased. Okay, that's why we are using FPGA. This is FPGA. So this flow we already seen. So I told you, no. So what are the target devices? ASIC and FPGA. Okay. So ASIC stands for application specific integrated circuits. Okay. This is only for specific application only. Okay. FPGA means so why you are using means it will take low power, and for improved speed we will use this ASIC. Okay. So this is basically our IC, which is used only for the specific application, specific purpose only. Okay, as I told you, like your household applications like TV, refrigerator, okay, and you have washing machine, automatic washing machine, okay. Some ACs application also. Example you take. So your ACs 5 years below ACs, you are operating with some remote. Now ACs are came, some company ACs, Lloyd I think so. So you can operate with your app also. Okay, those are nothing but IoT. Smart ACs came. Okay, so with IoT, with app, wherever you are outside, you can operate your AC which is present in your home. Okay, smart ACs are came. Okay, so you can't convert this olden AC into new AC. This is made with what that application only. We can't change. Okay, so that's why we call as ASIC. Okay, this smart bikes also. Okay, one smart bikes like Ather came. Ather, this is a electrical bike. Okay, electrical bike. So electrical bike, there is an application. In that application, you can see like the location of the bike and battery position, and what is the health of that vehicle. All those things you can see in the electrical vehicle. Okay, electrical vehicle. But normal bikes you can't see. Okay, so that is also one ASIC. Okay, and FPGA means I told you, field programmable gate array. FPGA, so that we can reprogram with collection of hundreds of thousands of logic gates. It consists of thousands of logic gates are there. Okay, and we can reprogram. Okay, that is FPGA. So FPGA flow, if you see, like you have Xilinx Vivado. This is one EDA tool which is given by Xilinx company, AMD company. Previously, Xilinx was one company. Now AMD has acquired the Xilinx. Okay, first you need to write the HDL code, hardware descriptive language, HDL code. Okay, I told you, no. So this way, like this tool, whatever the tool, so this will do the synthesis. Synthesis is nothing but you are converting into your code into gate level netlist, gate level netlist hardware. Okay, suppose if you design some like counter, how you will design synchronous counter? You'll write the present state, next state, and you write the excitation values. And for each and every excitation values, you'll draw the K map. After getting that K map, you will get the logic expression. From the logic expression, you'll draw the logic diagram. Suppose you are doing manually, you are writing the code for this your counter. Tool will take care of this. Tool will calculate whole the table and K map and all those things, and it will generate the netlist hardware. Okay, so Vivado tool converts HDL into schematic. I told you, no, gate level netlist. Okay, and next it will do the implementation. Implementation means in the implementation it will translate. Okay, it will translate, it will map, place, and route. Okay, so whatever the floor planning, routing, placement, so that we seen in the physical design. No, so that physical design, so mapping will be done in the implementation. Okay, after this implementation, it will generate the bit file. It will generate the bit file. Okay, so bit stream is nothing but our electronic ICs will understand only zeros and ones. No, only zeros and ones. It's like a hex file. Okay, suppose in embedded also, microcontroller also, for the microcontroller or processor, at last, suppose if you are interfacing some LCD display or stepper motor. Okay, you did in the lab, I think so. At last, you'll write the program in assembly language, and you are generating the hex file, and you are loading into the microcontroller. So based on your application, your microcontroller will work. Okay, same like that, that bitstream file you are loading into FPGA. Okay, so bit file generation and hardware management. Okay, that will be loaded into the FPGA. Okay, so this is FPGA flow. So you need to see for design closures also, like functional closures. Functional closure means uh, you need to simulate whether your functionality is matching or not by using waveforms. You need to simulate, okay, whether your functionality is meeting or not. Okay, and power closures also. Power closures means proper timing closures, you need to see, and power efficiency. Okay, that you need to see. And timing closures means you need to study about this static timing analysis. I told you, no, you are studying about propagation delay, setup time, hold time, and violations, and clock tree synthesis. All those things will be taken care in static timing analysis. And clock domain crossing. Clock domain crossing means till now in digital you studied about only one single clock. Even it may be synchronous counters or register, shift registers, or FSMs, single clock. So some designs are there like asynchronous FIFO. Asynchronous FIFO, it consists of two clocks. So multiple clocks. When you are studying about multiple clocks, there will be some different. Those will be not synchronized. Okay. So study about the multiple clocks is nothing but clock domain crossing, and study about the resets. Okay, resets are basically, reset is also very much important. There are like asynchronous reset and synchronous reset. Okay, asynchronous reset and synchronous reset. Again, these are two types: asynchronous active low reset, active high reset, asynchronous active low reset, and active high reset. Okay, so in industry, what reset we are using? Okay, why not other resets we are not using? So what about the resets? Resets also very much important. The front end. Okay, that is nothing but timing closure. Okay, and next, if you see the course overview in the front end, so two courses are there. One is RTL design, and next one is ASIC SOC verification. RTL design, if you take, so we'll teach digital electronics. Okay, and next we'll teach Verilog. Okay, mainly Verilog. Verilog projects will provide, and will teach HTA, clock domain crossing, and reset domain crossing, and linting also will teach. Okay, that is in RTL design. Suppose if it is SOC verification, we'll teach digital electronics, we'll teach Verilog. Okay, we'll provide one project in the Verilog, and after that we'll teach system Verilog and system Verilog assertions, and UVM will teach. Okay, this is in the verification. Okay, till here common for both RTL design and ASIC SOC verification. Okay, two modules are there: RTL design and ASIC SOC verification. Okay, coming to Verilog and VHDL. Verilog is a high level HDL, easy syntax, easy to learn, and multi level abstraction. So basically, it will follow C syntax. If you are comfortable with C, so you can easily write the Verilog code. You can easily study about the Verilog code. Suppose Okay, this is Verilog. And coming to VHDL, VHDL, VHDL is nothing but very high speed integrated circuits hardware descriptive language. Okay, so this is hard syntax, controlled language, hard to learn, multi-level abstraction is there. Okay, this will follow the old language like Ada and Pascal, old language. Okay, Ada and Pascal. I think you don't have idea. These are the old languages. So this is standardized around 2001, and this is standardized around 1999. So this is very secure. So mainly used for defense purpose. The defense mostly in FPGAs we are using this VHDL. This Verilog uh, we are using in corporates for R&D purpose. This is global. Wherever you see, wherever you go, this RTL engineers they will use Verilog only. And if you take one example, suppose if you take one AND gate is there. AND gate consists of what? A and B, and Y equal to what? AB. Okay, this I know. Okay, so if you write in the Verilog, okay, these are two HDLs, hardware descriptive language. So whatever you design in the digital, you are describing in the textual format. Okay, in programming part is nothing but HDL, hardware descriptive language. Okay, so module and my module name. This is my what is my module name? Module name is module name or identifier we can call and underscore gate, and inputs and outputs you need to declare. Input A comma B. Okay, output Y. I need to use a continuous assignment statement, assign. Okay, Y equal to A and B. This is data flow modeling, DFL, data flow modeling. Okay, so Y equal to A and B. This is bitwise AND operator, bitwise and end module. Okay, end module. So within how many lines my code is completed? 3 lines of code is completed. Suppose if you take the VHDL, library IEEE, use IEEE dot std logic 1164 dot all. This is header file declaration. And in the entity, you need to declare the inputs. Entity and underscore gate is port A in std logic, B in std logic, Y out std logic, and underscore gate. Okay. And in the architecture, you need to write the logic. Okay. Architecture of and underscore gate is begin Y equal to A and B end architecture. Okay, so like how many lines of code is there? I think around 12 lines of code is there. Okay, it's a very hard syntax and a very complex, hard to learn that. Okay, it's a easy learn. So within 3 lines of code, my code is completed. Okay, this is the difference between Verilog and VHDL. Okay, so this is analog layout. I told you know, like in the VLSI, there are two things are there, like analog engineers and digital engineers. Okay, so digital engineers will some hundreds or thousands of transistors are there. Analog people can do. Okay, and so if we have millions of transistors, okay, some thousand crores of transistors, they need to go for digital flow. This is ASIC flow. Okay, ASIC flow. Analog layout is basically these analog people are doing with respect to transistor only. Okay, they are working under the transistor only. That too MOSFET and that is CMOS. Okay, so CMOS, they are working under the CMOS layouts and all those things, stick diagrams and all those things. So they will study. They will. Yeah, so if you are taking analog layout, so you need to study about floor planning, placement, matching, design rule checks, routing. Okay, DRC and LVS, post layout simulation, and tape out. Okay, all those things you are going to study in the analog layout. So same thing, floor planning means we need to see about the area and mass devices, resistors. Okay, so these analog people are working under the transistor. Okay, placement, matching. Okay, so here you have the CMOS transistor. This is a schematic, and how you are getting the layout. Okay, layout like this. So they will see and matching this placement, matching and base DRC. like this. Okay, routing, connections. Okay, same thing in physical design. We are seeing the how the global tracks are there and routing is happening and all those things. Design rule checks. They will see the design rule checks. So common errors they will see. Like there are so many metals are there, metal layers are there, like metal one, metal two, metal three, and N well like this. Like this they will see in the tool. Okay, common LVS issues they will see in the analog design. So analog layout concepts means like CMOS fabrication. They will study about. You need to study about CMOS fabrication, electromigration, IR drop, antenna effects, crosstalk, deep well, latch up. There will be a latch up. Latch up concept is also there, and like HTA, charge channel effect, LOD, standard cells, memory layout, analog blocks. These are the concepts of analog layout. Okay. AMS is nothing but analog and mixed signal. Okay, these people will work both with analog as well as digital. Analog as well as digital, they will work out. Okay, so they will start schematic design, simulation, placement, routing, design rule checks, layout versus schematic. I told you, parasitic extractions. Parasitic means resistor RNC. Okay, and post layout netlist simulation. All those things they will study in the AMS. This is fully developed analog RF layout. Okay, ASIC and chip design flow. I already explained this. Okay, so coming to the Gnanodaya VLSI technology, we have a premier institute for advanced VLSI studies. Okay, it's located in Bangalore, Martali, opposite to Multiplex Bangalore, and also it's there in Hyderabad, Hyderabad SR Nagar. There in SR Nagar, near SR Nagar metro station. Just a walkable distance only. Best in class infrastructure and lab facility. So faculty are 15 plus years of experience in semiconductor domain and proven track record for the placement and scholarship facility. So coming to the unique features, 100 plus and placement assistance will be given and industry standard course curriculum is there and VPN support will be given. Okay, low cost for for money. Okay, and wherever you see we have a VLSI, healthcare, automotive, telecommunication, consumer electronics. Wherever you see VLSI is booming like anything. Okay, so many opportunities are coming within 1 or 2 years. Okay, and coming to the placement process, first we'll take the requirement from the client and we will assist the student for the resume preparation and all those things. And we'll send the resume to the client. Okay, after shortlisting and so for attending the interview, so we'll send the student to attend the interview and after that final selection. Okay, this is my placement, our placement process. And this I told you about product-based companies. Eligibility should be BE BTech with a EC and triple E. So why EC and triple E means in this you will study about analog electronics and digital electronics. Okay, these are the main foundation subjects for VLSI. If you take any domain, okay, either it may be one second, either it may be PD, DV, or RTL, analog layout. Okay, any domain you take, these are the basic subjects. So in the foundation, basic subjects you need to study about this. Okay, and you will study about Tickle, scripting language, and Linux, STA, static timing analysis. Fab also will tell. Fabrication, VLSI fabrication. As a design verification or PD engineer, you need to have an idea how the chip is making. Okay, that fabricating. That you need to have the idea. These all things are come under the basic modules. Okay, basic modules, and tool related means based on the PD, you'll study about all those things, floor planning, partitioning, and if it is DV means you will study about the programming part only. That is Verilog, RTL design, Verilog, system Verilog, UVM, and all those things. Okay, or minimum MER, MTech, minimum 60%. Good communication skills should be there. Okay, it should be good communication skills and training process is registration, discussing fee and course. Training period, mostly training period will be 6 months only. preparation with mentors and conducting mock interviews. Okay, so every week, mostly on Fridays, you have assessments. Assessments will give 30 questions, and will assess, each carries 1 mark and 1 hour time, and will assess your, after completing that concepts, they will give assessments. Assignments also will give, like, 2 questions will give, and you will check your understanding of descriptive part. Okay, there itself will review, and after completing one module, will conduct one mock interview, and also will conduct one technical seminars. Okay, and aptitude seminars also. Okay, we'll check, means this is a continuous process. We'll check your, we'll try to improve your communication skills. Okay, by these activities. Okay, and 100% placement assistance will be given. Okay, and these are the top companies. Okay, mm, companies are there in our institute. Okay, like multinational companies, Intel. I think from our managing director, I think January or February, Intel and AMD is coming to our institute for placements. I think so. So the sir told that Intel and AMD is coming. Okay, for design verification and physical design. Okay. So even though product-based companies are also coming, and want to take the our students. Okay, EDA companies, some startups, like Infochips, Tisal, Mirafra. Okay, service-based companies like SCL, TCS, Wipro, Capgemini. Okay, so Capgemini's company, they will, for women's, they are providing a special drive. Okay, so for women's, there will be opportunity for Capgemini. Okay, special drive will be conducted, basically for the VLSA only. For the women's only particular for women's. Okay, this is one of the opportunity for women's Capgemini, and these are the company. These are the students who are joined, who in one of the success from our Gnanodaya Institute. Amar Gopal, so he's design verification. He got placed in Apex. Ram Babu, Capgemini, Sham, LNT. Okay, and so Reshma HCL. So like this, Soumya, Capgemini. Okay, so like that. So many Anjali L&T, okay, Sai, Ambient. These are our success students who successfully placed in the different companies, okay, different companies. So if you take the training and intake, so there are like total three are there. Physical design, this is back end. Analog layout, okay, this is analog design. And ASIC verification is front end, okay. So physical design is 6 months, and analog layout and verification is 4 months. Daily 1 hour class and lab practice will be given, okay, for all this. Weekend batch means 6 hours per week, and lab practice will be given, and intake is 15 to 20 students only. Okay, and whatever the lab is there, VPN lab access will be given, and we have 15 plus experienced faculty who are academics as well as industry experienced. So tool related thing will provide from the industry persons only. Okay, 100% placement support you will get. uh, Placement support will be given till you got placed. Okay, these are the training and methodology and intake. So this is our contact number. You can contact. Okay, this is our email ID and website. We have app also. So Gnanodaya VLSI app in the Play Store and App Store, that you can install, and you can enroll for the course, and so many like some modules are available, and you can enroll in that also. Okay, this is about today's session. Yes. Yeah. Any doubts or any queries in this session?